Alrighty, there's one last thing that I want to talk about, and it's this thing called simple harmonic motion. So this is a phrase that physicists use. They say that an object, where if its position can be described by a sine function or a cosine function, then we're going to say that's in simple harmonic motion. Let me just give you some examples of what they mean when they say that. They might mean like I don't know if you're on like a swing. Oh, I'm not a very good artist, so I don't know why I'm trying to do this. But if you're in a swing set and you kind of go back and forth, right? And you're gonna swing all the way back here, and then you're gonna swing all the way over here, and you're swinging, and your position over time. If I were to track like number of feet forward or number of feet forward backwards, and if I were to plot that over time, I might start usually start back on the swing. So maybe my position is negative, and then I'm gonna swing to the middle. I'm gonna end up here in the middle where my position is kind of zero in the middle. And then I'm gonna swing forward. So my position is gonna go up. And then I'm gonna swing to the middle again. And then I'm gonna swing to the back. And it's gonna keep going like that, right? Eventually it'll settle down because of gravity. But if we just say that there's no gravity or not because of gravity, because of friction, it's just gonna slow down. But if maybe we were in a world with no friction and you started on a swing set and you went like this and you never let your feet touch the ground, then you're going to keep swinging and keep swinging and keep swinging. And a lot of times in experiments, physicists will set up a situation where they use a lot of oil and grease. So they really minimize the friction and they can get nearly a frictionless scenario where they can almost get this to go on for forever. Another common example of this is going to be a lot of times physicists will put like a weight on a spring. So maybe I have a spring hanging, and maybe if I stretch the spring out and put a big weight on that, if I stretch that spring out and put a weight, what's going to happen as soon as I let go? It's going to bounce up, right? But then it's going to bounce back down because of gravity, and it's going to bounce back up and bounce back down. And so the spring is going to kind of go back and forth between like being really wound up and being really stretched out. We're going to go back and forth. So again, if I were to kind of think about the position over time, maybe I'm starting with my spring way down at the bottom, and then my position's going to increase over time, and then it's going to go all the way up to the top and all the way down and all the way up. And it's just going to keep doing that. Boom, 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 right? But I'm going to spread this graph and make a sine wave because I want to think about it going over time. So anytime that an object's position is described like this, we call it simple harmonic motion. Okay, there's two phrases that we want to think about here. One of them we already kind of use. They talk about the period of the motion, 2 pi over omega. We've used a phrase a lot like that before. The omega is a little bit different here. A lot of times we've been using b as like the multiplier in this function inside of the sine or cosine, but a lot of times physicists will use omega. That's a Greek letter. It's kind of a curvy W, omega. It's just like the B. You could call it B if you wanted, but I just wanted to show you that sometimes physicists will use omega instead. So the period is 2 pi over omega, just like we're used to. And again, the period is the amount of time that it takes to complete one cycle. So how many times it takes to go from here to here. And then a really important other property here is what we call the frequency. And the frequency is actually omega over 2 pi. It's the reciprocal of the period, and the frequency of the motion is the number of cycles that happen in 1 unit time. So the period is going to be like, how long does it take for this to happen? And the frequency is going to be, okay, I'm starting my stopwatch now. How many cycles do I get in a minute? Or how many cycles do I get in a second? Or whatever time unit you're using. Okay, so that's the frequency. It's the reciprocal of the period. So this example here, example 3, I have a ball attached to a string, a lot like this situation here, a spring, and I'm pulling it down 6 inches, and then I'm going to release it. And it turns out resulting in harmonic motion with a period of 8 seconds. And what I want to do there is write an equation for the ball's simple harmonic motion. Okay, so there's 2 facts that I know here. I know that I'm pulled down 6 inches, and then I know that the period is 8 inches or 8 seconds. Okay, so if we have this spring and I pull it down 6 inches, how far do you think it's gonna bounce back up? It's also gonna go like it's gonna go back to the middle, but then 6 inches up more. So it's gonna go if I went kind of at my neutral and I went down six, then I would go back up and then go up another six. It's like kind of an equal and opposite thing. So when I have this spring moving like this, I'm gonna go all the way down to negative 6 inches below kind of my neutral, and then all the way up to 6 inches above my neutral. So that tells me that my A is 6. Well, really, it tells me that my absolute value of A is 6 because I still have to decide if there's going to be a reflection or not. And I kind of feel like there's going to be one because see how this looks a lot like my sine, or it looks a lot like my cosine graph, but the cosine's at the intersection is down here, and my normal cosine has the intersection up here. So I think that actually A is going to be negative 6 because we're stretching down instead of up. So I know my amplitude. Now I need to figure out the other pieces. So I have an A and I have an omega. I need to figure out, or a B, right? Well, I'm told the period. I know the period is 8 seconds, but I also know that the period is equal to 2 pi over omega. So this 8 needs to be equal to 2 pi over omega, because that's the formula for the period. And so I can use this to solve for omega. How am I going to do that? I don't like that my omega is in the denominator, so I'm going to go ahead and multiply omega on both sides of the equation, which is going to clear that out. That leaves me with 8 omega is 2 pi. I'll divide by 8, and that will give me that omega is pi over 4 when that reduces. All right, so now I'm ready to write a function here. I don't have to deal with like a shift because I'm really starting at neutral, so I'm not like kind of moving this up or down any. And I'm starting my clock when I'm at the minimum, so I don't have any like phase shift either. So my equation is going to be y equals negative 6. Let's see, do I want to use sine or cosine? I want to use cosine because we're not starting at the origin, we're starting at the bottom. So cosine of pi over 4 times t, because that's my omega. And now just using these two pieces of information of like the original distance down and the amount of time that it takes for one cycle to occur, now I have a whole model, and I can use this model to answer questions like, what will the position of the ball be at 2 seconds or 12 seconds or all these different points of time? Or what time would it be when the position is at this amount? Now, kind of that backwards of that would require solving an equation that we haven't learned how to do yet. But later in the semester, we'll figure out how to do those things. All right. Another thing that we could think about here is how many cycles will happen in 1 minute. So how many times will it go up, down, up, down, up, down in 1 minute if it takes 8 seconds to do one cycle? What I might do to think about this is go back to the frequency. We're defined on the top that the frequency, which is omega over 2 pi. This is the number of cycles per unit time. And let's see, because we did things with seconds, my unit time is in seconds. So it's really going to be per second. Let's figure out what omega over 2 pi is and see if we can use the number of cycles per second to help us figure out how many cycles happen in a minute. So omega over 2 pi is equal to pi over 4 over 2 pi. I'll need to multiply by the reciprocal here and call this pi over 4 times 1 over 2 pi. That'll reduce, and I'll end up with 1 over 8 cycles per second. Cycles per second. So I get an eighth of a cycle in a second. But that's not quite what I'm asking for. I want to know how many cycles happen in a minute. So I'm going to have to do some conversions. And maybe you've done something like this in chemistry before, where I might say, hey, in 1 minute, there are 60 seconds. And this is a way to change our units. So I'm going to be able to cancel out those units of seconds. And I can do this because 60 seconds and 1 minute are actually equal to each other. And let's see, I'll get 60 over 8, or what is 60 over 8? 60 divided by 8. 7.5. And the units on this now are cycles per minute. 7.5 cycles happen in 1 minute when the period is 8 seconds. So that's one thing that's actually really cool about knowing the period. If you know the period, if you just take the reciprocal of the period, 1 over 8 ends up being my frequency. So period was 8, frequency was 1 over 8. But then I did want to convert this into a different unit just to interpret it a little bit more. All right, those are just a few examples of real life phenomenon that can be modeled with sines and cosines, but there's all sorts of them. Anytime that something is repeating, kind of going up and down and up and down and up and down over and over again, it can be modeled with a sine or a cosine. And so I encourage you to look around the world around you and see, are there any measurements that I'm experiencing right now that are going up and down and up and down and keep repeating? And could I model them with a sine or a cosine? And maybe let me know what you come up with. All right, take care.